Okay, good evening, everyone. Thank you for joining us this evening for our second part of the NLPC's workshop, SDS4299. So I hope all of you had dinner already because we might end approximately in 2 hours time. So let's start. So this workshop, SDS4299, is the second part of the two-part series workshop hosted by the workshops department at NUS Statistics and Data Science Society. So we'll be going more into applied natural language processing using deep learning and neural network. So before I go into the content, if you have any questions for us during the course of the workshop, please head on to Slido with this code and key in your burning questions there. We'll try our best to answer any questions you have regarding the workshop. Okay, I'll first introduce our team for this workshop. So, Vinod.
Hi. Hello, I'm a year 3 BZA student.
I'm Keith. I'm year 2 business analytics as well.
Hello, I'm Bharat, a year 2 data science student. Nice to meet you.
So the three of us will be hosting this workshop for this evening. Okay, so firstly, let's recap what went on in the previous workshop in SDS1101. So we covered text pre-processing methods like word tokenizing, stemming, part of speech tagging, and we went into naive Bayes classifier as well. And we ended off by training a naive Bayes classifier and evaluating the results. So if you can't remember the results, we actually pasted it here. So as you can see, the naive Bayes model actually performed very well, quite decently. So we got a good result, but can we do better? So we can definitely do better, and that is the whole point of this workshop actually. So we are gonna improve the accuracy of our model using different models, in particular, like specifically deep learning models. So natural language processing is definitely hard. The reason why it's hard is because machines can't understand language, but us humans can. So why is it so easy for us to understand language? So it's very obvious because of our brains. So we are wired to be able to learn and understand language, whereas machines don't actually have a brain, which is why they can't understand language as well as we do. However, we can try to mimic how our brain works, and that's how neural networks come into play. So the first part of this workshop, I'll be introducing neural networks. So the introduction to neural networks is not, I won't be going very in-depth into it. I'll introduce core concepts because this is setting the foundation for later on in the workshop so that you can follow on when we go to the coding portion. So let's jump straight to it. So neural networks were inspired by neurons. So if you don't know what a neuron is, this is actually how it looks like. I took it off the internet. The important things to know is the dendrite actually. For the rest of the characteristic of a neuron, I'm not gonna say anything about it because I do not know as well. So the dendrite is important because that's where the neurons pass signals to one another. And these signals are what allows us humans to learn. So this is how an artificial neural network would look like. So each circle, each node represents a neuron actually. And there are 3 main layers in a neural network. So first off is the input layer. That's where the raw data gets fed in. The second type of layer would be the hidden layer. So there can be multiple hidden layers in a neural network model. The reason why we call them hidden layer is because we do not actually observe what's going on in those layers. Finally, there's an output layer, which gives the predictions. Okay, so let's go deeper into a neuron, which is called a perceptron in this case. So I'll show you a very simple neural network model containing 2 input neurons, X1 and X2, and 1 output neuron. So this neuron, or also called perceptron, is basically a binary classifier, meaning that it gives off 2 outputs. So in this case, we will say that output is 1 or 0. It takes in 2 inputs, X1, X2, and it assigns weights to them, W1 and W2. So what this weights means is that it assigns an importance to the feature. each neuron takes in one feature. So in this case, since we have two input neurons, there's two features, and the weights corresponding to the feature shows how important that feature is. There's also an additional parameter called a bias, denoted here as x0. By default, it has a value of 1, and it has its own corresponding weight, w0. So what the bias does is that it actually helps to shift the activation function. I'll go into detail about activation function later on. But think of this bias as analogous to the constant term in a linear model. I'm sure you guys are familiar with the linear model, y equal mx plus c, the constant term being c. What the constant term does is that it transposes the linear line by a constant amount. And this bias in a neural network is analogous to that. It shifts the activation functions and helps the neural network fits better to the data. So these are the weights. And what the neural network will do is that you'll get a weighted sum. So it takes the W0 multiplied by bias. In this case, bias is 1, so it's just W0 alone, plus x1 multiplied by W1 and plus x2 multiplied by W2. So once we get the weighted sum, we apply this weighted sum to the activation function to give off an output y hat. So I'll go into the activation function now. What is an activation function? It's basically a function that determines whether the neuron should fire or activate. So the most simple activation function that I will introduce to you is the step function shown in the diagram here. So the function states that if x is negative, your output 0, whereas if x is positive, your output 1. That's why it's actually called step function. So in this example, the x would be the weighted sum. So the neuron will activate and output 1 if the weighted sum is positive. So simple as that. There's two main types of activation functions, a linear activation function and non-linear activation functions. We'll be introducing to you a few non-linear activation functions because the non-linear activation functions are what gives the model its complexity, more complexity. So the first non-linear activation function would be the sigmoid or logistic activation function. As shown on this graph here, the output is bound from 0 to 1, and this is good for predicting probability because probability has a range from 0 to 1 as well. The second type would be the hyperbolic tangent activation function. It's similar to sigmoid, but the range is actually from -1 to 1. So what this means is that negative values get mapped to the negative values get mapped more negative, while the values close to 0 will get mapped to 0. And last but not least, there's a ReLU activation function, also known as a rectified linear unit. So it's actually a piecewise linear function where the negative values will be mapped to 0. So these are the three common and main types of non-linear activation functions. Okay, so I'll move on to quantifying loss. Why is quantifying loss important? So if you are familiar with machine learning, like a simple linear regression model, we always have the cost function, and the cost function is what tells us how well the model is performing. So for example, in linear regression, the most common cost function would be the mean square error or the root mean square error. Similarly, neural networks also have cost functions for us to determine how good the model is. So there's two main types of problems that we face, either a regression problem or classification problem. So different problems have different cost functions to quantify our loss. For regression, the common cost functions would be the mean square error and the mean absolute error. For classification, it's a binary cross entropy and a hinge loss. For the rest of this workshop, we will assume a classification task with binary cross entropy as our cost function. There's a formula for the binary cross entropy. Don't worry about it. You don't have to memorize it or anything. It's just for you to know. So what the binary cross entropy does is that it measures the distance between the predicted probability distribution and the ground truth underlying distribution. So you'll see later on in the code how this plays a part. Next up is an important concept known as gradient descent. So in very simple terms, gradient descent is an iterative solution to optimize the loss. When we say optimize in this case, we want to minimize it. Okay, so in order to give you the intuition, let me give you an analogy. So imagine you're standing at the top of a mountain. You want to get to the bottom of the mountain as quick as possible. So what you do is that you look around and you find the steeper slope. Because the steeper the slope, the faster you can get to the bottom. Am I right? So you look around, you find the steeper slope, you take a step forward. Once you take that step forward, in your new position, you look around again, you find in which direction the steeper slope will be, and you take that step forward again. You keep on doing this until you reach the bottom, where the ground is flat and there's no steeper slope anymore. So this is the intuition. This is actually the intuition as to how gradient descent works. So in a slightly more mathematical explanation, let us say that the direction of the steepest descent represented by a vector v. Then we have to move some distance alpha in direction v. This distance alpha is the step forward that I said when you want to take to move downwards. Once you finish that step, you check again for direction of steepest descent, and you keep doing until you stop the minima. So this alpha term, the step forward that you take, is known as a learning rate. So this learning rate is something that we have to define, and it's not an easy task because when the learning rate is small, it comes with some set of problems, and when it's too large, it comes with its own set of problems as well. So in the leftmost diagram, you can see that when the learning rate is small, the point over here, when it moves downwards, you can see that it takes very, very small steps until you reach the minimum. The good thing is that you can be sure you will reach the minimum, but you will take a very long time. On the other hand, on the other extreme, look at the right graph. When your learning rate is too big, you might completely miss the minimum, and you might even move in the wrong direction. So we have to pick the learning rate that is just right, such that we can reach the local minimum as quickly as possible. So as you can see, if it's too small, it takes too much time. If it's too high, you actually diverge, you miss the local minimum. So for gradient descent, we undergo gradient descent in order to update the weight. The reason why we update the weight is because we want to minimize the loss. So we consolidate every individual weight in the network into a huge column vector, and we update this column vector by taking the original column vector of weights minus the learning rate multiplied by the vector. So if the alpha is set right, we should be able to reach a minimum, and we should be able to tweak our weights to minimize the cost function. So in this way, the weight will keep on updating until you reach the bottom. And when you reach the bottom the gradient will be 0. The weights will stop updating, and that's when you reach the minimum. Okay, next important concept will be the backpropagation. So we have defined gradient descent and the learning rate, but we need to calculate the direction of the steepest descent, as we denoted as v. So on the graph here, this is a very simple graph, I'm sure all of you know. It's a quadratic function. So how will you calculate the gradient of this quadratic function? So I'm sure all of you learned before in calculus, the gradient can be calculated by taking the derivative, the slope at a point. So this is for 2D plane, so very, very simple. But we need to generalize to n dimensions in a neural network. So this is a more complicated task. So in order to introduce to you the intuition behind the backpropagation, I will show you the simplest neural network you'll ever see in your life. So this neural network consists of one input neuron, one hidden neuron, and one output neuron. So it gives us an output, it gives us an output, and we can calculate the loss denoted as L. So these neurons come with its own weights, W1, W2. So what we want to know is that how does a small change in W1 affect the final loss L? So the reason why we want to find out about this is because we want to tweak the weight such that the loss is minimum. So in order to do that, we have to figure out how a small change in the W1, the weight, affect the final loss. And as you know from calculus, we can do that from taking the derivative. So we actually apply the chain rule here. dl dw1, you can dissect it using chain rule into dl dy hat multiplied by dy hat dz1, which is the activation function, multiplied by dz1 dw1. And this chain rule will give you the value of dl dw1, which is the small change in w1 that how the final loss L will be affected by a small change in w1. So this seems relatively simple, like just a simple chain rule. It's because this neural network is very, very simple. So your neural network will never look this simple. There's going to be a lot of hidden layers with multiple neurons in each layer. So the math will be very tedious. Hence, in order to show you how the backpropagation works, I am showing you this very, very simple neural network for you to understand how the chain rule works in this case. So, as you can see, the output is actually being propagated backwards, such that the weight will be adjusted. And this is why the term is called backpropagation, where the output flows back to the input. So you repeat this for every weight in the network using gradients from later layers. Okay, so the flow of information backwards, hence the term backpropagation. So the algorithm take the derivative, which gives a gradient of the loss with respect to each parameter. You shift the parameters in order to minimize the loss. Okay, so you run the backpropagation algorithm for each weight in the neural net to get a gradient. Using this gradient, you take a step, improve our network slightly, and you finally stop when our cost function is minimized. Okay, so last but not least, I'll introduce to you what dropout is. So if you're familiar with machine learning, you will be familiar with the term called overfitting. So this happens when your model memorizes the training data. So this can occur in a neural network. And in order to prevent that from happening, we apply a dropout. So at every iteration, we randomly select some neurons and remove it with all the incoming and outgoing connections. The probability of these neurons will be selected depends on the rate specified. So you can actually see this later when we show you the code. So to visualize better, if you see, you can see the standard neural net on the left. Every neuron will take in the input from the previous layer and give its own output to every other neuron in the next layer. So after applying dropout, you can see that some neurons are removed and all their incoming and outgoing connections are removed as well. So this actually prevents overfitting of the data for neural networks. So that's actually the end of my introduction to neural networks. I hope you have a slightly more understanding of how it works, because you need to know this for the upcoming part when we apply it for natural language processing. I'll now pass my time on to Vinod, who will go through what embeddings are.
Okay, so thank you, Keith, for the rather extensive explanation on deep learning itself. So now I'll go through the second part, which is embeddings. So this is pretty much one of the crux of today's workshop. So first of all, we have to ask ourselves this question: what exactly is embeddings and why do we actually need them? So embeddings are essentially low-dimensional continuous vector representations. Or in other words, it's an array of numbers that represent every particular word. And the reason why we actually need embeddings is because we can't simply put words or feed words into a model. In the event you wanted to create a machine learning model that predicts the friendliness level of any particular word or sentence, you can't just simply feed hello into that model and expect it to produce an output of 1 to represent that it's friendly. What you actually need to do is to convert this word hello into a string or a series of numbers, or in this case, an array of numbers, and then subsequently feed that into the model in order to produce an output. This series or this array of numbers is what is in a machine readable format and can therefore be fed into the model. So when we talk about having an array of numbers to represent words, naturally a lot of us will think of one-hot encoding, am I right? So in one-hot encoding, there's only one step, which is to create a vector for each unique word that we have in our corpus or in our data set. So for example, let's say we had a sentence of 4 words: I love data and science. If you were to one-hot encode it, you'll get this matrix that you see on your right. So essentially, each column of it represents one particular word. So the first column corresponds to the word I. So it's represented by this vector notation 1, 0, 0, 0. And the third column naturally represents the word data. So it goes by 0, 0, 1, 0. So, likewise, columns 2 represents the word love, and column 4 represents the word science. So the question is, we have such a nice vector representation over here, can we use this and feed this into a machine learning model? In other words, is this machine readable? The answer is yes, you can feed it to your machine learning models. But just because you can feed it doesn't mean it's a good embedding. Is it a good embedding? No. What is the reason why this isn't a good embedding? I think there are three main reasons why it isn't. Because first of all, as the number of words increases in your corpus, the number of dimensions of our vector also will increase proportionately. The computational complexity increases and the time taken also increases manifold. So in our earlier example, we had a sentence of 4 words only. And you realize that the number of dimensions of each of our vector was also 4. So let's say we increase it to 1,000 words in our corpus, or in other words, 1,000 words in our data set. The number of dimensions of our particular vector is also going to increase to 1,000. And 1,000 is not a lot of words, In a lot of training data sets, you're going to see a lot more words in your, a lot more unique words in your data set. And therefore, the number of dimensions of your vector is going to increase hell of a lot. And as a result of that, the time taken will also increase exponentially. The second reason is that these vectors, these high dimensional vectors that we have are also sparse. Sparse in the sense that out of, let's say we had 1,000 dimensional vector, out of this 1,000 elements, 999 of them will be 0, and only one of the elements will be a 1. And in a lot of machine learning models, such as your deep learning models that require backpropagation, having a sparse matrix or a sparse vector, it doesn't really help, and it doesn't allow you to train effectively. And therefore, the accuracy of that model will suffer as a result. And the third problem and the third issue is that there is actually no semantic similarity between any one of your vectors. Semantic is basically refers to the vectors being able to capture the meaning of the words itself. So I'll show you what this means in the form of a diagram. So ideally, you want all your vectors to be able to capture the meaning of your words. So if we take a look at this 3D plot that I have over here, on your on your left-hand side, you see this 3 words in green: goose, eagle, and bee. These 3 words are similar in the sense that, okay, I'm sorry, this is just a temporary file alarm. Give me 30 seconds, it will go away. All right, sorry, that was just a fire alarm test. It happens every Wednesday. Okay, so the 3 words here, goose, eagle, and bee, they refer to animals that are able to fly. And therefore, these words are grouped together. On the right-hand side, we see another 3 words in blue: helicopter, drone, rockets. So these are also very similar in the sense that they are actually referring to man-made equipment that are close together, and therefore they are grouped closely together. And you notice that these 2 groups, animals and man-made, they're actually pointing in 2 different directions, away from each other. However, if you were to one hot and code all these words like goose, eagle, bee, helicopter, drone, you might end up having eagle pointing in the same direction as a helicopter, or similar direction as a helicopter, and a drone pointing in a similar direction as an eagle, which is not what you want, because that means that the vectors don't actually accurately capture the meaning of the words. So some of your other embeddings are able to do this, and this helps improve the accuracy of your machine learning model. So what are the different types of embeddings that are available to us? So there are actually 2 main groups that we are looking at. First is what we call pre-trained embeddings. So pre-trained embeddings are embeddings that have been trained on a large data set. And what we'll do is that we'll essentially borrow these vectors that have been already trained on this large data set. And so, for example, if you have a sentence of 4 words, you'll find the word that corresponds this particular word in that particular dictionary, in that pre-trained embedding, and then borrow that particular vector and use that to represent your word. So you will not be training or customizing your embeddings to your own data set. This is slightly different from custom embeddings, which you guys actually encountered in the previous workshop, where you use TF-IDF. So these embeddings are specific to your own data set. The pre-trained embeddings will be the focus of today's session. We'll be exploring 2 main ones: glove as well as word2vec. So you'll see that in the next couple of slides. But before that, there's always this very interesting question that people like to ask, which is, when do I use the pre-trained embedding and when should I use a custom embedding? And generally, the consensus is that if you have a very small data set, then you'll benefit a lot by having a pre-trained embedding. However, if you have a very, very large extensive data set, then your model might be actually able to perform better with custom embedding that is fine-tuned to your own data set. You can explore this in your own time as well. So now I'll just go through the basics of word2vec before moving on to the Google Collaboratory Notebook, where you will get to apply your knowledge of word2vec into this particular IMDb dataset. So word2vec is essentially a single layered neural network based embedding model that was created back in 2013 by researchers at Google. There are two main algorithms. One is CBAL, the other one is known as skipgram. CBAL basically stands for continuous bag of words. So in this particular algorithm, what happens is that the words before and after your target word are given as inputs to the model, and then the model will predict the probability of the target word occurring. So example, if you have a sentence of 6 words, I really love studying data science. And this is the third iteration where the target word is actually love. What you would do is that you look at the words prior to love, which is I and really, and you'll look at the words after love, which is studying and data, and you'll feed these 4 words as inputs to the model, and the model will predict the probability of love occurring. Likewise, in the next iteration, when you move on to studying, the context words would be really and love, as well as data and science. These 4 words will be the inputs to your model, and the model will then predict the probability of studying, and it will do its fine-tuning accordingly. On the other hand, if you look at skipgram, it's like the other way around. The target word in the previous algorithm will now be given as an input to the model, and the model will then predict the probability of neighboring words occurring before and after it. So using the same sentence as before, if your target word is now love, it would predict the probability of I really studying and data occurring. And in the next iteration, when it looks at studying as the target word, it would have actually predicted the probability of really love data and science occurring. So when you have 2 algorithms that have different number of inputs and outputs, for example, in combined vector of words, you have 4 inputs, 1 output. In skipgram, you have 1 input, 4 outputs. So they look totally different. In fact, they're the opposite of one another. So how do these 2 algorithms come together? The thing is, we're only actually interested in one part of the entire model, which is the weight of the hidden layer that connects to either the single input or the single output. So in the case of continuous bag of words model, we are interested in the weights that are connecting the hidden layer to the output. In the case of skipgram, we are interested in the hidden layer weights that are connected to the inputs. So if your hidden layer has 50 neurons in it, what you'll end up having will be 50 weights for each particular word, and that weights for each particular word will be your vector. In the case of skipgram, if you have 100 neurons as the hidden layer, the 100 weights that are attached from the input to the hidden layer will then be your vector, a 100-dimensional vector for that particular word. So as you have seen, it's really the number of dimensions of your vector is really dependent of the number of number of neurons you have in your hidden layer. And this is something that you can vary. In Glove, what happens, in word2vec, what happens is that there are a bunch of them. The typical number that we're looking at in the pre-trained would be 300 neurons. So you will be experiencing, or you'll be using a 300-dimensional vector to represent each particular word. Glove, on the other hand, it's slightly different. It was created in 2014 by researchers at Stanford itself. Glove basically stands for Global Vectors for Word Representations. Global vectors will be the words that we'll use to generate the word glove. What happened is that in addition to the semantic similarity that the word2vec takes into account, it also takes into account the frequency of each word occurring in a corpus itself. We won't be going into the mathematical details behind these 2 algorithms. What we'll be looking at will be the hands-on practical segment with the Google Colab. This is where we will try and apply the vectors from Word2Vec as well as a glove and apply it to this particular data set known as IMDb. So if y'all could do me a favor and head over to this link, you'll be able to open up the file that we have, the Google Colab file. I believe Bharat has also sent the link. So please head on to that link. So once you're here, what I want you guys to do is to first of all, click on File and click on Save a Copy in Drive. File, Save a Copy in Drive, because I don't want you guys to lose out on the changes that you have made in the event that you make any changes. Because if you do not save a copy to Drive, you'll be making changes in playground mode. Is everyone okay? All right. We'll begin our Google Colab component. So first up, in this Google Colab file, we will be going through some more advanced machine learning models for NLP using Python. So first up, you'll learn how to use the various embeddings to vectorize our words. Basically, the two types of embeddings we're looking at will be Word2Vec as well as glove. And you will also build 3 additional advanced sentiment classifiers. One will be your basic RNN, LSTM, and transformers. You will find out what these are in a moment. So first up, I want you to, you will have to run this 2 lines of code to actually install transformers and data sets. They will be used later on. Okay, but just take note that this is not a hands-on segment, so we will not be expecting you to click run on any of these lines of code because it will take a very, very long time to run and you wouldn't be able to sit around and wait for it to actually complete. So we'll just be looking at the outputs that have been already run and produced earlier on. Okay, so the next part, we'll be looking at importing the relevant libraries. So first up will be NLTK, stop words. I think most of you who have attended the workshop 1 will be familiar with this. So stop words are basically the words that we do not wish to have in our text. We will just remove them, words that do not add much meaning or such value to the particular sentence. We'll be also using NLTK to tokenize some of our words later on. We'll be importing the standard NumPy for linear algebra. We'll also be importing pandas because that is what we'll be using to read our data file, our CSV file, and we'll also be using pandas to store our data in a data frame format. URL library.request. Okay, we'll be using this particular library to actually retrieve our glove zip file directly from the Stanford website. What Stanford has done is that they have actually have had all the different types of embeddings, 50-dimensional, 100-dimensional, 200-dimensional, and 300-dimensional text files, all zipped up and made available online. And we're going to be retrieving that directly using this particular library. The next one will be Genism Downloader. So this is similar in the sense that we'll be using this to download the pre-trained Word2Vec embeddings. SciPy Spatial. Okay, so this is actually for us to calculate the Euclidean distance between the vectors. Earlier on, I talked about how your vectors capture the semantic similarity. And I'm actually going to prove that to you later on with an example. And this is where the spatial library will come in. The next would be train test split from the sklearn library. This is a very standard method that I think most of you will be familiar with. Metrics, will be importing accuracy score as well as the classification report to give us a more comprehensive understanding of the performance of our model. And last but not least will be all the TensorFlow relevant tools as well as the entire library itself. So we'll be using a lot of these subsequently to build our deep learning model. So first up, what we need to do is to read our data using pandas. So for those of you who attended our first workshop, you probably have this data set already. Otherwise, you can actually head over to this link and download it yourself. And once you're done downloading, what you can do is run this line of code in your free time, not now, and then click on choose files and upload that particular file. It takes quite a bit of time to run, so just take note of that. Next, you can read it into a pandas data frame and take a look at it. So for those of you who have seen this data set before, you know that this is clean, but not very clean. There are still things that we need to do in order to pre-process the data and make sure that it's in a format that we can feed well into the model. So one of the biggest issues that I think most of us would have noticed with this data set is that because it was scraped from online sources, there are a lot of break tags that are still present in the code itself. So that's what we're going to remove at first. So in this pre-processed block of code, what we're doing is that we are splitting up the X data and the Y data. So the X data will actually be your reviews. The Y data will be your sentiment scores. So in the X data, what we want to do is to remove the break text and then rejoin all of it. So we'll take the sentence, remove the break text, and form the sentence back again. As for the Y column, what we want to do is to convert the positives to 1 and the negatives to 0, so that we can feed these as labels to our machine learning model later on. And that's what we'll be doing in the last line over here. Next, before we do any further pre-processing, we are going to split up our data into the training, validation, and test data. So we're going to split it in such a way that we have 60% of the data that is kept for training purposes, 20% that is kept for validation purposes, and 20%, which is the remaining 20%, that is kept for testing purposes. So that's what we're doing with these two lines of code. 0.4 means that 0.6 is kept for training, and the remaining 0.5% is split into half. So 0.2 for validation, 0.2 for testing. So if you run this line of code, you just have you'll be able to notice the couple of lines that are associated with the training data itself. And you notice that the indexing is all jumbled up. That's because we have split up randomly, and therefore the indexing has also changed. So let's just take a look at the size of our training and test data, training and validation data. So the training data is actually consists of 30,000 sentences, and the validation data consists of 10,000 sentences. And because the test size is also the same size as the validation data, it's also of size 10,000. So the next major step that we need to do is to actually remove our stop words. So what I've done here is that I've actually imported the stop words from the NLTK library and specified that I wanted the English stop words. And I've also extended this list of stop words with a lot of additional punctuations and random words as well, because these are the words that we noticed were being used that do not actually give much meaning to some of the sentences earlier on. So we will be also manually removing them because these are not actually captured by these current list of stop words that we have imported. Next, we're going to pre-process it one shot. So there's a lot going on in this function. So we're going to explain it step by step. So what we're essentially doing is that for each sentence, we're going to use the word tokenize function to split the sentences into individual words. Then afterwards, we will check that each lowercase version of that individual word are not present in stop words. If they're not present in stop words, good. If they're present in stop words, we'll ignore it and move on to the next word. And then we'll make sure that we keep the lowercase version of those words. So what's going to happen is that now, instead of a sentence, you have a list of words that are not present, that are lowercase and not present in stop words. We're going to be applying this function to your training data, your validation data, as well as your testing data. So this is what your sample output will look like once you have gone through this function. Now, the next part, this will take a bit of time as well. If you're going to run it on your own later on, you're going to have to request and retrieve this particular zip file, glove6b zip. And once you unzip this file, like I mentioned previously, there are actually a couple of text files. The one that we're going to be using today will be the last text file, because this is actually of each of the vectors here are of 300 dimensions. If you want to, you can actually use the 50-dimensional or 100-dimensional text files as well. It's really up to you. So how we will use this zip file was that we will actually make a dictionary of this zip file, where the keys will actually be the words itself, and the values will actually be the vectors associated with those particular words. So what we're going to do is that we're going to open up this text file. We're going to go line by line. Each line will look roughly like what I've shared in the comments over here. The first element will be the word itself, and the subsequent elements on that line will be the rest of the 300-dimensional vector. So what we're going to do is we're going to split up such that it becomes a list. We'll keep the first element of that list because that corresponds to our word, And the rest of the list will actually be the 300-dimensional vector that we will store in this variable known as vector. And lastly, we'll put this word and the associated vector into the glove dictionary. When you run len glove dictionary, you realize that there are actually 400,000 words in our dictionary. That's a lot. So now we come to the fun part actually, which is similarity of the words. I talked about semantic similarity earlier. We want to see how similar certain words are to one another. So this find similar word function, what it does is that it's going to calculate the equivalent distance between the word that you have chosen, as well as all other words in the library, and find out what are the, and sort it out according to how close each word is to this chosen word that you have. And it's going to return you the list of all the nearest words in sequential order. So when you run this function on a word like pencil, for instance, and you print out the top 10, you realize that actually the top 10, many of them, the first few especially, they are very, very, very similar to the word pencil. Pencil itself is the closest. Pencils, crayon, ink, watercolor. See, they're all very related, aren't they? Some of the next few words are a bit cryptic, so we will skip that. But when you move on to laptop, you see a similar pattern as well. The most similar word would be the word itself, followed by laptops, computers, cell phones, portable phones. All these are words that you typically associate with laptop as well. So actually, indeed, our glove embeddings have actually accurately captured the meaning of each individual word. So I hope you can try it with any other word that you like as well, and you'll probably see a similar outcome. So this is definitely a step in the right direction. What we need to do next, before we move on to the modeling step, is to tokenize our words. But before that, we will just specify a few things. One is that we want to keep the length of all our sentences to 100 words. And we only care about the first 100 words. So in the event that it's less than 100 words, we will take care of it slightly later. But in the event that it's more than 100 words, we will want to ignore the remaining few words. This is to make sure that all the number of words in our sentences are all standardized. The maximum number of words is all standardized. And that the model does not take too long of a time to run. And the max words actually that we have written down as 100,000. This actually corresponds to the total number of words that we want to keep in our tokenizer. So for now, we only care about the first 100,000 most frequently occurring words. The others will not be kept. So that in this block of code, what we're doing is that we are importing the tokenizer object from the TensorFlow library. And we're going to convert each word in our sentence into a number. So the first word will be converted to the number 0, the second word will convert to the number 1, etc. So there's like an indexing that's occurring over here. Train sequences, validation sequences, test sequences, these are the variables that will be used to store all these tokenized sentences. And like I mentioned earlier, we want to keep all our sentences to 100 words. But when we run and we check the sizes out, we realize that some of the sentences are actually huge. Like for example, the second sentence has a length of 509. The first sentence has a length of 274. The third sentence has a length of 194. But they're also on other cases, on the other extreme, and there are some other sentences that are actually much shorter than 100. So in order to standardize it and fit it into a neural network model, what we're going to do is that we're going to do padding. Padding is basically a process whereby we make sure that we standardize the length, whereby the shorter length sentences will be 0 will be appended to it such that it's of length 100. And we'll do a post padding, which means we will add the zeros to the back of the array. And for those arrays that exceed the length of 100, what's going to happen is that the rest of the sentences will be truncated and removed. So when you apply this function over here, this is the output that we'll notice. So every array is actually of the same size of size 100. Okay, so here's the interesting part where we will actually create the embedding matrix that we will feed into the machine learning model. The embedding matrix is going to be of 10,000 rows and 300 columns, because 300 corresponds to the embedding dimension of our vectors earlier. And the max number of words will be the number of rows that we have, which is 100,000. So what we're going to do is that we're going to iterate through every word in the tokenizer, and we're going to check if that word exists in the glove dictionary. If it does exist, we will update the matrix by removing that array of zeros and then replacing it with this 300-dimensional vector in that particular position. Once we're done with this, we can proceed to building the simple neural network model. So we're going to create a sequential model using the sequential API. The first layer is going to be embedding layer. So this is very standard embedding layer code that you've seen earlier. The only difference is that what we're going to do is that we're going to set the weights using the embedding matrix that we have created earlier. And we're going to change the dot trainable and set the trainable equals to false because we do not want backpropagation to update the vectors that we have gotten from glove itself. What we'll do next, we will be flattening it. We'll add a 32 neurons in our dense layer, and we have an output layer of 1 using the activation function, the sigmoid activation function, because we want to produce it, check whether it's a 0 or a 1. And when we print out the model summary, you notice that they're actually these 4 layers that we have created earlier on. What we'll do next is to compile the model using a binary cross entropy loss function. And we'll use the Adam optimizer so that we do not have to specify the learning rate. And we'll add in additional metrics to check out the accuracy score of both our validation and the training data sets. And you'll fit the train data as well as the validation data to this particular model. That's what's happening in the last line. And when you generate your predictions, you realize that it's not performing too well. It's giving you an accuracy score of 0.49 at the moment. Let's try something different, which is word2vec. So in word2vec, we are doing essentially the same thing. We are extracting the pre-trained word2vec model as well as the associated vectors for each word. And in order to get the vector associated with each word, you can't use the .get function. What you need to do is to actually index it directly using the square brackets. And this is also a 300-dimensional vector, as you can see over here. The length of each vector is 300. If you want to print out the entire vector itself, you can do so over here as well. I've done the word hello, and the vector associated with it is printed over here. Now, this is the exact same step to create the embedding matrix as we have seen earlier. The only difference here is that because you can't use the .get function, it will, in the event that the word does not exist, it will throw you an error. And in order to deal with the error, we have a try and an except block. So similarly, if the word does exist, we will go back to your embedding matrix and we'll update that one column with this new vector. If the word does not exist, we will move on and leave that particular column as a column of zeros. Now, this is the exact same lines of code that we have seen earlier, just that now instead of using the original embedding matrix using glove, you'll use embedding matrix 2, which corresponds to the embedding matrix created with word2vec. And after we have trained it using the exact same lines of code, we realize that the performance is pretty good, decent at 0.78, though this is still worse than your naive Bayes model that you've seen earlier. We'll see if it's possible to improve this as we go on through the rest of this collab notebook. But in the meantime, what we're going to do is we're going to take a short break. We'll take a short break for about 10 minutes. So please come back at 8:05 p.m. Thank you.
Okay, welcome back everyone from break. So we'll carry on with our workshop. Right now, I'll introduce to you recurrent neural networks, in short, RNN, and how they are different from an artificial neural network I introduced to you earlier. So recurrent neural networks is a special type of artificial neural network that is adapted to work for time series or data that involves sequences. So this is why it's good for natural language processing, because spoken language sentences are essentially, you can think of it as sequences. So how this works is because RNNs have the concept of memory that helps them store the states or information of previous inputs to generate the next output. So this concept of memory and how they store the states will be introduced to you soon. Okay, so this is how the recurrent neural network technically may look like. Like this is a visualization of how it will look like. So the RNN takes in input at time step t, denoted as xt, and it'll give out an output yt as well. At the same time, it'll have an internal state denoted as ht, and this internal state will be updated at every time step. So this internal state is a memory mentioned earlier, where it is able to store information from one time step and pass it on to another time step. So this is different from standard neural networks because the standard neural networks go from input to output in one direction, also known as feed forward. However, RNNs has loops in them, which allows information to persist over time. And these loops is essentially what you are seeing here, where the internal state is being updated and passed to the next time step. So like what I described earlier, at time step t, the RNN takes in input xt and computes yt. It also computes an internal state ht and passes information to the next time step ht+1. So let's unfold an RNN for easier visualization. Okay, so this is what you see just now. By unfolding it, it looks something like this. So think of this as copies of the RNN network at each layer. So at the first layer, at time, let's denote it as time step t minus 1. The RNN takes in the xt minus 1, it outputs yt minus 1. At the same time, it updates an internal state ht minus 1 and pass it on to the next layer. The next layer will take in this input ht minus 1, this internal state, and its own set of inputs xt, and output yt at time step t. So this occurs in the next time step as well, where it updates its own internal state at ht and passes it on to the RNN at time step t plus 1. At time step t plus 1, the RNN takes in its inputs at t plus 1, denoted as xt plus 1, and gives out an output yt plus 1. So this, you can see that this internal state is being updated and passed on to the next time step. So this is how RNN actually keeps a memory in a sense, and this memory helps, and this memory pass on information from the previous sequence to the next sequence. So how they do this is through the recurrence relation. So the recurrence relation is applied to every time step to process the sequence. So this is a mathematical notation. So it might look familiar to you. So at ht plus 1, the internal state at time step t plus 1, it's calculated using a function that takes in as input xt, the inputs at time step t, ht, which is the internal state at the previous time step, wx, which is the weight of the features, and wh, the weight of the internal state, as well as a bias. So this function will look familiar to you because this is the activation function. So as you can see, it takes in an extra input compared to the standard neural network, which is in this case ht, the previous time step. So this is how it calculates this is how it updates the internal state at the next time step. And just to take note, the same function, the same activation function and set of parameters are used at every time step. So earlier on, I introduced you backpropagation in the standard neural network, where the errors are passed from output to input backwards in order to update the weights so that we can achieve the minimum loss function. So in RNNs, we call it backpropagation through time. And it's different because in RNN, there's different time steps involved. So this is an unfolded RNN I showed you earlier. So at each time step, it actually, when it outputs the y at time step t, we calculate the loss at that time step as well, denoted as L. We sum up all this loss and find out what the total loss is. After finding the total loss, the errors are actually backpropagated through the time steps. So this is different from the standard neural network because the standard neural network backpropagate the error through a single feed-forward network at a single time step. But in this RNN, each error is propagated at each individual time step and finally across all time steps where we are until the beginning of the sequence. In this way, the gradient will keep changing, will keep multiplying at each time step until the beginning of the sequence. So this is how the backpropagation through time is different from the backpropagation introduced to you earlier. Okay, so let's go back to the Colab and see how the simple RNN model is implemented. So the code over here was what we ran. So the code is similar to what you saw earlier, from what Vinod showed you earlier. The only difference is that we add a simple RNN layer. So let's go through this. First, we define a sequential model. We add the embeddings. In this case, it's a word-to-vec embeddings. We set the layers, we set the weights as an embedding matrix 2. We set trainable equal to false. And instead of adding a dense network, we add a simple RNN network with 16 neurons. We also add a dropout of 0.5. And lastly, we add the output layer with the activation as sigmoid. We call the summary of the model. We can see the different layers in the model. So we compile with the loss function as a binary cross entropy using the Adam optimizer. And we feed the model with the train data and the variation data using 4 epochs and batch size of 16. So we predict using the test sequences. We get the classification report as per the previous model. And what we get is actually surprising. It's actually a lower accuracy score from earlier. So right now we have an accuracy score of 57%. Earlier was 78%. So this simple RNN model is actually performing a lot worse. So we can definitely improve on this. And Bhairav will show you how, where he will introduce a new RNN architecture called the long short-term memory model. Bhairav, on to you.
Yep. All right. Thank you, Keith. All right. So now you might be thinking, all right. So just I know that there's not very many of us over here. So feel free to unmute and ask me questions when we're going into it, because this stuff is a bit complicated and it would be better if we had a bit more interaction in this rather late session. So now you might be thinking, okay, fine. Why did we bother incorporating the sequential data when the model didn't perform as great as we hoped it would, right? Well then, here's the thing. RNNs are great, but then they do have their issues. What issues? We'll get to that. But we'll be able to address these issues using the next modification to the RNNs, which is known as the LSTM, or long short-term memory. Now, what does this mean? We'll get to see that as well. Now, let's begin. Here's the main problem with RNN. Backpropagation through time is great, but then let's consider the gradients that we have to use. So because each RNN depends on, because each output of the RNN depends on the input that comes at every single time step. And since the weights end up being sort of dependent on the sequence of inputs that you feed in. So you have to keep multiplying tons of gradients together in order to get in order to go for gradient descent and so on. So at first you start off with a decent sized gradient, and then you see that it starts to get smaller, then even smaller, and then eventually the gradient slowly vanishes. This is actually a big problem in RNNs because the gradients slowly end up vanishing. This is known as the vanishing gradient problem, and it's a real issue with RNNs. What ends up happening is that you end up multiplying by a small number so many times that the gradient just becomes zero. So what, you might say? So what if the gradient is zero? Well then, neural networks learn using the gradient. So does anyone want to tell me what happens if the gradient vanishes? The network doesn't learn. So what ends up happening is that the network actually only becomes focused on the last few inputs of our sequence. So it forgets whatever it was told at the beginning, and it only remembers the very last few words. They have the average attention, they have the attention span of the average Twitter user. So the network has an extremely short-term memory. So how do we fix this problem? Well then, we have to add some memory to the RNN, don't we? How do we do this? Well, then we have to forget the less important stuff and carry forward the more important stuff. Basically, we just have to implement the concept of a long-term memory inside our RNN. Now, how do RNNs exactly work? So you basically have them passing along something known as a hidden state from each time step to the next. So what ends up happening is that you have H1. Then you, in your next time step, you pass on H2, your hidden state with input 2. Then you have H3. And so on and so forth. The information of the past is carried along by the hidden state. But we already know that the hidden state in RNNs is dominated by the recency bias. So here's the key idea. We will carry along H, which carries the local info. But while passing along this hidden state, we'll pass along a cell state as well. This cell state will carry the most important info from the past. All right. Now, here's the anatomy of the LSTM. Here is the anatomy of an LSTM cell. I know it seems complicated, but it's really simple in practice. Let's break it down, shall we? So there are 3 parts to the LSTM cell. You have 3 gates, as they are called. You have the forget gate, which gets rid of the info that you do not need anymore. You have the input gate, which updates the cell state with the information that has come in now. And then you have the output gate, which basically gets the new hidden vector for you to pass along. All right. So now here is the forget gate. Hi minus 1 and xi. So these are the hidden state at the previous time as well as our current input. We'll add the two together to get hi minus 1 plus xi. Then we'll pass it to the sigmoid function. Then on passing to the sigmoid function, we'll get to the forget vector. This vector encodes what previous info that we need to forget. So what ends up happening is that the sigmoid will basically compress everything to between 0 and 1. Closer to 0 means you forget. Closer to 1, remember it. Make sense? All right. So now let's move on to the input gate. So the input gate will take in hi minus 1 and xi. We'll add the two together. We'll pass it into the sigmoid function to get something known as the input vector. We'll also pass it into the tan h function to get something known as the candidate vector. Then what we do is that we multiply the two together. The multiplication of these two yields the increment that we must update the cell state by. Effectively, what we're doing over here is that we're taking the information from the past and we're taking our current information and we're basically figuring out how much we need to change the cell state by given this new information. All right. Now, here's how we apply this update. So you have the forget vector and then you have ci minus 1. So you multiply the two together. This basically tells ci minus 1 to say, okay, fine, forget the information that I tell you to, remember the information that I tell that you have to. Now, you have this update, right? So all you have to do is to just add these two together. Fi times ci minus 1 plus ii plus c prime I. So what ends up happening is that this becomes our new cell state. This becomes ci. This gets passed on. All right. Everyone following me so far? All right. You can unmute if you want. This stuff is a bit involved. All right. Now, here is how the output gate works. So you have ci going into the tan h function. Then what we do is that we pass in our hidden state plus xi into the sigmoid function. We multiply the two together to get our new hidden state. So the hidden state carries along some information from ci, it carries along in more information from the past, and it also carries information from the present using hi plus xi. So this becomes a new hidden state that we pass along. Now, let's put it all together to consolidate our understanding of this issue. So you have ci minus 1 coming in over here. You have hi and xi being joined together to get hi plus xi. So this first part over here is the forget gate. So hi plus xi goes into the sigmoid function, becomes fi, the vector of stuff that we need to forget. This then gets multiplied with ci fi to do part of the update. Now, let's move on to the input gate. So hi plus xi gets passed into both the sigmoid as well as the tan h function, right? So we get the input vector and the candidate vector. We multiply the two together to get the update. Then we add the update to our cell state to get our new cell state, which gets passed on over here. Now, the new cell state comes into the tan h gate. The hi minus 1 plus xi goes into the sigmoid gate, it goes into the sigmoid function. We multiply the two together to get our new hidden state. So you basically have the new outputs being ci and hi, which will go on to the next hidden state, and so on and so on and so on and so on until we basically get to the end. Now, I'm aware that this may all be rather abstract, but here let's get our hands dirty. Let's actually look at the practical demo. Everyone can see my screen, right? All right. So here is the model 4. So as you can see over here, we basically, again, we just set the training weights to be the ones for Vertebrek. We set them to be non-trainable. We add the LSTM model. We add a layer of 16 LSTM cells, and we add a single dropout layer. Then what we do is that we run this for 8 epochs, so the batch size is 16. And then looking at the prediction classifiers, we can actually see that we get a really respectable score of 87% accuracy, which is quite an improvement over our previous record. All right. So now that everyone is following so far, right? So now you might think that, okay, fine, yeah. Can everyone see my screen now?
Yep.
All right. Yeah. All right. So in that case, let's move on. So now let's move on to the current state of the art, because we data scientists are never ever satisfied, no matter the accuracy. As long as it's not 100, we'll want more. How do we get more? Well, transformer models are how we get a higher accuracy. So let's pay a bit of attention now, shall we? LSTMs are wonderful, they're great. However, they take ages upon ages to train because you have to run through the computation one by one by one by one by one. You can't parallelize it. They don't exploit the nature of GPUs that we have now. So they have issues training, and they still have some issues in training longer sequences. Well then, the reason why they have issues in training longer sequences is that they still use all of the info of the sequence. Now you might be thinking, Bharat, you maniac, why? What are you even saying? Why are you telling us that now adding all of the information of the sequence is now bad? Well then, I have my reasons. Consider the following. Consider a machine translation task, a sequence to sequence task. What we were looking at, what we were assuming before was a sequence to a single output. What about a sequence to sequence task? Well then, you have an input, right? I am a human, right? Then you basically lead it into an output. So this is basically translating it into Portuguese, right? So this is a machine translation task, seems pretty standard, right? Well then, the position of each word of each output vector will matter in this case. What ends up happening is that, suppose for the first part of the output, if you want to translate it, the first input, I, will matter a lot more than the last input, human. The issue with LSTMs and other RNN architectures is that they pass along only the encoder. They only pass along one hidden state. So what ends up happening is that they only pass along a summary of the entire record. They don't actually tell you what happens at what time step. So this basically means that we lose some information while we're trying to deal with this. Make sense? So what we need to do is that we need some way to account for each individual input along with the context. So here is one common model used for this before we got to transformers. This is the encoder-decoder model, which basically is just two LSTMs joined together. So you have an encoder LSTM that converts the input into a fixed length representation. So what they usually do is that they basically take whatever input that you have. It will be a long string of inputs. They will basically condense it into one single vector. This one single vector goes into another LSTM, which converts this fixed length representation into an output. So this is great for sequence-to-sequence tasks, but it's not the best. So here's how they work. So you have the encoder sending along the context vector to the decoder. The decoder will then use this context vector to get the output. What transformers do and why they're so amazing is that they actually pass along every single intermediate hidden state from the encoder to the decoder. So this is exactly why this gives transformers their exceptional efficiency. Now, you might be thinking, all right, so how does this work? Well, here's the idea. We'll use the context vector plus the hidden state at every time step in the decoder. So you'll have the decoder hidden state, right? Because the decoder, again, is an LSTM. Then you have the H1, H2, H3. You have the hidden states at every single time step. So from these hidden states, we'll have to compute the context. Now, how exactly do we compute the context? How do we know which hidden states are more relevant than others at each step of our computation? Because it's not guaranteed to be one-to-one. It's not guaranteed that the output is going to be the same length as the input. It's not even a guarantee that the input matters in the same direction as the output. So how do we even do this? Well then, let's take inspiration from search engines. So in search engines, you send a query. You basically have the query get matched to certain keys. And based on their matching to the keys, you get certain values. So what we do is that we basically take our encoder vectors. We will check them against the decoder and we will see the best matches, i.e. the values of the decoder. So what we do is that we multiply the query and the values together to get something known as a score. This whole scoring basis is the absolute base of the attention concept that is so popular in that is implemented in many transformer models nowadays. This is at the heart and soul of many of the more recent developments in NLP. So you might be thinking, where do we get the query vectors? Where do we get the key vectors? Well, then we get the query vectors from the encoder and we get the key vectors from the decoder. If anyone really wants to go do a deep dive on this, the paper Attention is All You Need, published in 2017, actually gives a pretty good explanation of this entire mechanism. It's actually the paper that started off this entire thing. So now, how exactly do we compute an output? Well then, for a particular output, we'll assign a score to each hidden state at every given point of time. This is done by a scoring matrix, as we have seen earlier. Now, what we do is that we will softmax the scores. Then we will scale the hidden scores by the softmax scores. All right. So then what we do is that we add the hidden states together. So can anyone tell me what exactly it is that we've done here? What is the intuitive meaning behind this? Feel free to unmute. Like, what do you think would be the intuitive meaning behind this? Well then, all right, so the intuitive meaning behind this is the scores basically tell you how important each of the hidden states are. By multiplying it with the softmax of each score, we basically weight the state, we weight each hidden state by how important they are in the output. So effectively what we're doing is that we're incorporating all the information, we're placing different weights on the information, which is a nice callback to how we first started with how neural networks work. Now, let's make a prediction. So the hidden state will contain global info. The hidden state of the decoder will contain the global info. We create a context vector which contains the local info based on the past. What we then do is that we add the two together to finally get the output at a given time step. Then what you do is that you just repeat this for every single time step of the output. And this, everyone, is the basis of how attention and transformers work. This is at the heart and soul of many of the models that we've seen today, that we will see going forward. And you've actually gotten a little bit taste of this attention mechanism in the very first workshop when they debuted GPT-3, which is built on this attention mechanism. More on that later. Let's first move to the collab, because I'm aware that this might have gone a bit too theoretical for everyone. So here, because it's a bit more complicated to implement transformers and TensorFlow, we opted to use the Hugging Face pre-trained transformers. So these are built on a version of transformers known as BERT. So now we're loading in the IMDb dataset in this slide. So then what we do is that we set up the tokenizer and then we pad and truncate the sequences that do not fit the input size for the transformer. All right. So this is effectively what we were doing at first. This is just pre-processing in a form that Hugging Face will accept. Now we will set up the train and test data sets, right? So the train and the test. Then we will load our pre-trained model. So this basically is the BERT base case model. This is pretty standard. Now we'll have to set up a training arguments file because this is a huge model. So while fine tuning it, we'll want to have checkpoints so that even if it disconnects, we are okay. Now, we will set up and run a trainer for the model. So this is basically fine tuning the data. You remember how we were able to fine tune our original Word2Vec model or glove representations with a pre-trained one? This is effectively what we're doing for a full model. So now you basically see that, all right, fine, you have all of these training steps right over here. And then we'll finally evaluate the new fine-tuned model. So you can see that we get a really great accuracy of around 93%, which is much better than any of the other models that we've tried. So the thing is that like paying attention actually works really, really well for this model. All right, so let's get back to the slides so that we can have a the last few things. So transformers right now are the current state of art models for NLP. In 2017, they were introduced. In 2018, they improved the encoding of transformers with BERT, which has many, many spin-offs now. Like I think Albert, Rosabert, and all of those are still like top of the line models, even though BERT is currently a bit obsolete. Now you have in 2019, you have XLNet and ERNIE as well as GPT-2. And then in 2020, OpenAI released GPT-3, which seems to be the current pinnacle of NLP models. However, this is a very, very developing field and further research is still ongoing. But what unites all these models together is the fact that they all use the attention mechanism and are transformer-based models. So currently the state of the art in natural language processing is the attention model, it is the attention mechanism and transformer models. So in conclusion, here is the basic summary of the results. Basic neural nets, we were able to hit about 78%. Simple RNNs, 57%, although I attribute that more to a lack of training epochs. Now, LSTM, we were able to hit about 87%. But please keep in mind that all of these networks are shallow. So what ends up happening is that we didn't actually want to use a very, very big data set. Most of these deep learning models actually shine with tens of hundreds of thousands of data points. Because we chose to use a limited data set so that we didn't ask everyone to download a 10 GB file or whatever, we ended up using a rather shallow model and a small data set. Now, if we look at the performance of our transformer models on this data set, though, you can see that it's far and above the best model of the bunch at 93%, which is rather good. All right, so here's a quick summary. So we did a brief recap on deep learning, and we just summed up the main parts of the NLP1 workshop. Then we looked into embeddings, and then we looked into RNNs, LSTMs, as well as the current transformer models. But now this is where you come in. We've given you the basic tools that you need in order to establish your own NLP project. So what you can do is that you could basically try and then improve upon the models that we had. I told you, right? We didn't really put our models to very many training epochs. We didn't use as many data sets. So you can try and source your own data. You could basically try and then experiment with more hyperparameters. You could experiment with different optimizers. You can start messing around with the model architectures, for example. So the possibilities are literally endless, even if you restrict yourself to only deep NLP. All in all, this area is like a massively exploding area, and there's a ton of interesting stuff to learn. So I'll be leaving that off. If anyone has any further questions for us, you can ask on the Slido, you can unmute and ask. If not, thank you so much for paying attention on a Wednesday night and coming and spending your evening learning about NLP with us. And this is Bharat from SDS signing off. Thank you so much.